got 7 people today from doing all sorts of different research in the department. I thought we kind of just kind of show you guys what we do here after a couple of years, figure out, and then you can take that as inspiration or take it a little further. So we're going to start with Patrick Boyce here, and what we're going to do is just have about 5 minutes talk from everyone. After the talk, while we're switching presentations, feel free to ask a question or two. But if you have a very pressing, long discussion, maybe keep it to the end after, right? And I think every student will give a little background on what department they're in, what professor they're working with, and their topics. And we'll just go from there, see how it flows. So, floor is all you, Patrick.
All right, good afternoon. I'm Patrick Boyce. I'm with CCOM. I'm working with Dr. Brian Calder on what I'm working, this is my working title, so towards the automation of volunteered and authoritative bathymetric data comparisons for reputation analysis, basically comparing 2 data sources to determine how well they relate to each other. So for those that are not ocean mappers, about 58% of US waters and about 79% of the world's oceans are yet unmapped to modern standards. And we're working in many ways to try to close that gap and consistently assess the data that we do have. One way that we could potentially do this is by essentially mobilizing the entire world's civilian fleet, right? So all of these ships and vessels, all the way down to your fishing vessel, may have a navigational sonar and a GPS on board, which could allow us to collect data for hydrographic purposes. In fact, it's already being done. So this is an image of the Data Center for Digital Bathymetry, which is an IHO or International Hydrographic Organization owned database. And it's hard to see here, but all these colored lines are track lines of vessels, which have been volunteered, which is why it's called volunteered bathymetric information to this database. But as of yet, it's not really used a whole lot because it's really difficult to tell how good this data is. It's also very time consuming. So Dr. Calder and Dr. Miles in the back have been working on a program that will automate this process. So currently hydrographic offices are doing this all in a very labor intensive manual process where they download the data from the various databases, they compare it, or they do any additional data management and any sort of waves or any tags applications or anything they need to do to that data manually, and then they do these comparisons manually. Dr. Calder has come up with a statistical way to automate this process, whereby comparing the BBI to some authoritative data source, you get a reputation. Higher reputation, we believe that that data is better. However, it still requires some manual downloads. You still have to go out to these databases like the one I just showed you, and wherever you're getting your authoritative data manually. If you're interested in how they're doing this, this is a link to that, to his last paper from 2021. So my thesis and project is to automate the rest of it. So getting this data, doing the data discovery, and then supplying that data to Brian's program so that essentially almost start to finish, it's an automated process. So we're looking to automate an API and Amazon Web Service search for whatever data we're looking for. The program assures co-location of the data by using GPS. So the location of the data, one of the metadata requirements is that it has GPS location. We have multiple ways to search. We can search by specific charts or vessels or an area on the globe. It's faster than manual process. We don't have to drive to any of these web interfaces. You don't have to open a web page or anything like that. So it's quite significantly faster to do the same thing. And then as a total proof of concept, we're doing it using the National Bathymetric Source, which in the United States is being created as the authoritative source for data that you'll see on a chart. So if you've ever seen a nautical chart, the NBS is a database that holds the best data that is being used for that chart. So this is what it looks like, the tool that I've created or am in the process of creating. Essentially, you have just a quick interface, which is sort of based on other NOAA tools and tools that have been designed here. Just asking some basic questions like, what are you most interested in? Do you want both data sets? How are we searching for it? And what do you want to get out of it? Where do you want me to put it? That kind of thing. Users can supply an area. So just by clicking and dragging or typing that area in, and then they can click run. And when they do, they'll be presented with this monitoring window as it's running. It gives status updates. Hey, I found this data that you've asked for, or I haven't. If it found it, where did it put it? And then we're done and it's complete, which is always nice to know. In the map window, it shows you, here's the area you looked for or you asked for. In green, here's all the charts that I found that intersect that area that you asked for. And in pink, the track lines that intersect that area that you've asked for, or the charts that you downloaded. This is just an example of one. There are actually 16 different ways that this program can be run, but it essentially all results in an area or a requested piece of data and everything else that's co-located with it for both volunteer bathymetric information and the authoritative source that you're going to compare to. In the end, and what I'm working on right now is connecting that, like I said, to Brian's program, so that the data that this collects gets fed in and mutation up. Questions? That was super fast, yeah.
Who's the volunteer data? What exactly is it comparing it to? Is it from NOAA, data from NOAA?
Yeah, so for the proof of concept, it's data from NOAA, and that, I should say, it's data that NOAA is using to put on the chart. So this is data that NOAA is saying, we trust this data to put on a chart, and it's the best for whatever that is. It could have come from NOAA ships, it could have come from contractors, it doesn't really matter. What matters is that NOAA says this is authoritative for whatever area we're looking at. In other countries, they may have a different type of database, but the idea is we could search whatever database they wanted to, depending on who's using the program. That's future down the road, but eventually that would be the case. So at least currently, all volunteer data comes from the DCDB. That's common globally. And then the authoritative data piece would be sort of selected by whatever hydrographic office wants to use the program.
Hi all, my name is Daniel. I'm a new student here, it's a master's degree. And my presentation today is not about my master's thesis, not yet, but that was a job that I did in Greenland, was a month last summer, from middle July up to August. So I did that job for the Ocean Research Project and mapped the gaps. So what I'm gonna do today, it's gonna be like a really brief introduction. And then I'm going to jump to the survey tools and specifications. And after that, I really want to share the challenges, mapping uncharted waters and the mapped areas pretty quickly, don't worry. So GOMARI stands for Glacial Ocean Mapping and Research Interdisciplinary Effort. It's one of the projects from a nonprofit organization, the Ocean Research Project. That organization develops a bunch of research expedition in remote areas for a fraction of the cost. If you use a vessel, it's very expensive to use sailboats. And for the 2022 expedition, one of the goals was mapping the seabed of uncharted glacial fjords. So here, that map the gaps just come into play. What is Map the Gaps? Map the Gaps is a volunteer-based nonprofit organization, including marine map professionals, students, industrial partners, and alumni from the Nippon Foundation JetCon training program, which means I'm one of them, year 17, and Tomer is also another one. Tomer and I, we are both responsible for collecting those data. And so, we went to south of Greenland, southwest of Greenland. We spent 30 days there. We were able to map 6 fjords and Tamjøs. That little dot here, it's a small town, village, actually, nothing at all. But works as a base for us. Food, grocery, showers, bathroom. Pretty good, I can't complain, to be honest. And, okay, and from that, let's see, Mahita. There she is, beautiful lady, 22 meters. You can see here, that's Tomer, just for scale. And you can see the size of the vessel, the sailboats. Pretty comfortable. You can easily call it as home. You know, we've been there for 30 days, 8 people. Can't complain at all, again. So for mapping, we use our Archosonic 2026. Here, that's the multi-beam. The multi-beam were mounted on a USM pole. Here is just locked in the horizontal position. And of course, if you need to map, if you want to map, you need to lock it in the vertical position. You need to be inside the water. And for the motion sensor was a Planex Wave Monster. And we got correction for the Marine Star G4 Plus. Not always, of course, we lost in some positions, especially close to the fjords. But anyway, it does sound nice, right? Okay, let's go, Greenland, amazing. It is, indeed it is amazing. It's that feeling, you know, just conquer the unknown. It is amazing. I have to tell this. But there are a bunch of challenges, and I would like to share just a few of them. The first, the mapping approach. So, if no one ever saw this, this is a nautical shots, okay? And here on red, it's one of the places that we went. So, sorry for the resolution, but here on those circles, it's a depth that we do know. So it's a safe place. Let's go there. We do know. It's a safe place. Let's go there. So we began surveying known depth, but a few minutes later, we were literally outside the shots. So just keep it, you know, let's just keep it doing this in a safe depth, and then we can extend. Let's go to shallow water, deep water, whatever. But that was the approach. And sounds easy? Yes, it is. But there's always something. Fogs, quite often. You couldn't see anything, nothing in front of you. And then you can think, okay, I can use radar. Of course you can. The radar, you're going to see all those rocks. You can see the glaciers. You can see those bergs. But we cannot see those small ones. And they are really, they're big enough to give us, to give us a headache. As a matter of fact, we did hit them like a couple of times, 3 or 4 times. One of them was quite big. I'm glad that that didn't hit the pole. It was on the other side of the vessel. I could hear the iceberg just rolling on the roof. Was like, oh my God, what's happened? We lost the forehead sonar. We broke our propeller, so we're sailing at 9 knots, and all of a sudden it was 3.5. That's fine. We ended up in Nuuk, went to the capital to fix it, so that wasn't the plan. And that's a video. Not sure if it's gonna. So you can see, like, just have inside the vessel. How was that? So just full of small bergs. It's just a nightmare. It's beautiful though, but it's a nightmare. Okay, and another challenge was unreliable shots. It's an example. We went to that place that was the last fjords, and for the shot was something around 35 meters, 40 meters. Take a look, 10 meters. I'm gonna survey an area, an entire area with 10 meters. It's gonna take me months to finish. But, a great team and hard work, we did it. We're able to do it. Now, let's just share a few areas. I can't do all of them. It's a short time. But we did map 6 areas, was 266 square kilometers, and 599 miles. So that's the one subfjord. It took a week here. We were able to map up to 600 meters here. Amazing place, lovely. Here on the upper branch, we can see it's a glacier that ends up into the ocean. Here in the middle branch, it's completely deglaciated. there is no ice at all. And here, just on the south, it's just retrieving. So it's a pretty cool area for the whole scientific idea behind the job. So another one was the Sermi-Largasot. Sorry, I have no idea how to pronounce this. This is in Greenlandic. But anyway, we couldn't get here. A lot of ice, was really a stressful time. And then I want to share another video. Was one of the coolest icebergs that I ever saw in that trip. Take a look at this. Yeah, pretty cool. And also here, in the middle of the night, I wasn't expecting that at all. The Northern Lights. Wow, during the summer, amazing. Look, you know, I wasn't expecting. It's summer. We're supposed to see this during the winter. Lovely, beautiful. So our last fjord, that was the Alumersat water challenge. Water challenge. The multi-beam. She did work pretty hard to see the bottom, to track the bottom. It was just a nightmare. But we did it, amazing. But another cool video, that's when we were like pretty close to the glacier. Just take a look of that waterfall. I couldn't believe. Take a look at this. This is a waterfall. So it was amazing. Like, can you imagine how many sediments just put in that place? It's amazing. Anyway, that's my last slide, and my take-home message is that one. We can collect from a sailboat good bathymetry data, reaching remote areas at a fraction of a vessel cost. And that's my presentation. Thank you.
While you were surveying, how often were you using sail power, or did you just switch the?
Inside the fjords, just mooring. But that's not all the areas we mapped it. We also did transit mapping, and for the transit map, yeah, we're sailing.
How'd you get involved in that project?
Map the Gaps. It's basically a nonprofit organization made with CHEP alumni. And quite often I just receive an email, you know, there's a job, and then I apply.
It's a good group to be in.
Yeah, it is. My life changing. I mean, yeah, last year not last year, this summer, I went to Guam, Philippines, Greenland, what else? Mexico, just with Map the Gaps. So, yeah, it's cool. It's a really nice project.
Okay, hi guys, thanks for coming. So I'm going to talk to you guys about some work I've been doing with John Hughes Clark, who's a professor here over at CCOM, who does the ocean mapping course. And we've been trying to remove We've been trying to remove wobbles for quite a few years now. And you've got some nice geomorphology here that we're trying to detect and maybe classify using rugosity. But you've got these artifacts that are just overprinted the data. And when we look at it, it follows the ship track along. So it's just following the vessel. There's nothing natural about it. It's systematic. So towards getting perfect data, we're going to try to remove it. So in the way of doing so, I'll talk to you about where we've come from and where we are now. And the first step was essentially creating a model. So we create a mathematical model which positions these remote detections on the seafloor. Now we have an array, transmits sound, receives sound at a later time when the sound goes through the water column, but it shoots sound out along these cones. But we need to know where are these cones located and where they oriented. So for that, we have a whole host of sensors. We have a GPS, we have a motion sensor. We also have different probes to get the sound speed through the water column. And all these combine to eventually allow us to position that trace. Now, what we found out is we don't know the opening angle along these cones. We just know this steering angle. So we have to calculate that subtlety, and we do that by intersecting hyperbolas. So this is an iterative procedure. It takes maybe 3 to 10 iterations, depending on the model. So it's a little slow, and that does have issues when we're computing tens of thousands of soundings to create these bathymetric maps that Daniel was just showing you. So we found out though that all our data isn't this nice, perfect recreation of the true seafloor. The reason for that, 2 decades ago, John Hughes Clark found out that there are a host of integration errors. So 6 errors depending on the inter offsets between the auxiliary sensor, so the motion sensor, GPS, and our multi-beam. And if we have any of these wrong, it creates this sort of periodic ribbing of the surface. So we get this undulation, which a lot of the oceanographers and people that do ocean mapping may have noticed in their data. So we want to know what the true depth of the seafloor is while we collect this wobbly stuff. And that wobble sort of occurs with the motion of the boat. So the boat's moving at the wave period, which is about 8 seconds, and we're moving forward at about 5 meters per second. So they have a wavelength on the seafloor of about 40, 50 meters in shallow water at least. So we want to optimize this system, right? We have bathymetry, we know all the input, we have a whole lot of numbers, and we want to use some calculus. So we have this mathematical model. We're going to use gradients essentially to minimize this residuals. So we have each beam gives us a depth error. We analyze every single beam relative to a reference surface. Now we don't know what the true seafloor is, so we're going to just use a quadratic approximation. So we just assume it's nice and smooth, can have a little bend in it, depending on where you are, if you're at the top of a hill in a valley somewhere, and you get a whole bunch of depth residuals. Now we're going to try to do a basic gradient descent method. So we're somewhere along this parabola. This is a one-dimensional case, but we're going to be in 6 dimensions, but it's the same concept. You just go downhill, right? But it's a non-linear approach. So you don't go to the bottom in one step. You kind of step around the minima. And ideally, if all your assumptions hold, which is a big ideal, you get to the true solution, right? Nice flat seafloor in this case. So this is what's happening with a whole survey. You don't have one window, you have multiple windows as your vessel kind of moves along through the seafloor. And because all the assumptions don't always hold, on assumptions of flat seafloor, good luck finding those all the time, but we have 6 parameters, and hopefully something like a law of large number occurs where all the solutions are distributed normally around the true mean, and we slowly converge to the true. And I kind of proved this for slowly undulating seafloors on my master's. But what happens is this is a real seafloor. So this is the motion up here. You got roll, pitch, heading, yaw. This is just a swath of data acquired from a vessel, and you've got a whole bunch of undulation over here. Now, what we predicted was, these are my 6 estimates of my parameters through here, time series of them, that as soon as you get to this undulation seafloor, the quadratic approximation breaks down, and you have variation in your parameters. So we want to use an asymptotic mean, so like the average of this whole line to essentially calibrate the data. But the sensible thing to do would be to remove this. So we created an automated method to essentially detect when the seafloor is bad and throws out the analysis. So using that more stable solution, we go from a surface that starts like this, but ends like this. Now there's still some wobble in there, so it's not perfect, but this is just one line of data. When we're surveying, we got a lot more than that. So this is a full day of survey. This is 8 hours of data, multiple lines going on here. I've forced all 6 integration errors into the system. The trick now is to pull them back out at the same time using this nonlinear technique. Now, what we're seeing here from the seafloor is the heterogeneity spatially. So this is a nice smooth areas. Quadratic surface is going to do pretty well here. You've got all this crap. So we don't want to actually study this sort of area. So this is what the wobbles kind of look like if you get a little zoom on it, but we're going to filter these all out using my automated rugosity detection method. And also, of course, we're going to throw out areas where there isn't a whole lot of motion, because there's going to be no wobble. There's no motion. So that takes us down to about half of the windows to analyze, which is good because, as I mentioned, the method is a little slow, it's iterative. It is a numerical procedure. So we start with histograms like this, and when I filter it down, we get a lot tighter histograms. Now, I know what the true solutions are. I forced them in there. These values are all within about 2 to 3% of the absolute magnitude of what I actually forced. And although with half the windows, the bias doesn't really change, we come down to the same mean, the uncertainties are often 2 to 3 times better, which just makes us more confident in our solution. So applying that parameters that I solved there, we can go from a data set that looks like this to this. And it's not perfect, again, because we have a bunch of assumptions that go into the model. And what we've started to notice is, this is actually from John. John's very into oceanography and what the water club is doing. This is the surface sound speed measurement in the same area. So here we have a tidal front coming in. This is the Piscataqua, right off Piscataqua. And this dense cold water comes in, and we have a 15 meter per second jump in surface sound speed through these lines. And I'm assuming constant surface sound speed within a window. So this is going to slow down our approach to actually home in on a solution. So we want the most efficient optimization method to best use the data that we do have. And a further thing that John's noticed is that when right at the interface of this tidal front, because you have the cold, dense seawater going over the nice river plume, that friction, you see right here, creates these little internal waves. So this is the barrier right here. And you've got this internal wave that literally occurs. Same thing happens on the surface, but it's a lot longer wavelength. Happens underneath the water surface in the water column. And what it ends up doing is creating this weird little wobble because it's actually the surface wobbling, and we don't model that properly in our ray trace algorithm. So it creates a little wobble, which in my high dimensional space of solving 6, 7 other wobbles, I could potentially solve for this as a function of the others. So we want to essentially avoid these regions too, not just the bad seafloor. We also want to avoid the bad water column, and water column data may be a good reason.
Hi everyone, I think I'm your first non-ocean mapper today, so I will not be talking about ocean mapping for those of you who like ocean mapping. I'm a PhD student in ocean engineering working with Diane Foster on sediment transport type processes. So I'm going to talk a little bit about my research today. So there we are over there in the corner. So just to give you a little background of the process that I'm studying, it's called momentary liquefaction. So when the waves propagate over the sand, the trough of the wave can actually cause an upward pressure gradient within the sand. And if that pressure gradient is large enough, it can overcome the weight of the sand and cause it to act like a fluid, essentially becoming quicksand. It loses its bearing capacity, soluble structures, which has implications, of course, for coastal areas and homes, like this little video that kind of shows you a little bit of it. If that weight is a house and that ping pong ball is underground pipe, those stuff would sink or come to the surface, which is something we obviously don't want. And this process is very well modeled in terms of modeling experiments and lab experiments, but not well understood in a field setting. Not many people have actual field measurements of it. So that's what I'm trying to fill that knowledge gap on. I don't want to go too much into theory, but there's certain equations that can actually describe momentary liquefaction. This is the one I generally focus on. It's got a bunch of sediment parameters on this side, and then your pressure gradient on the other side. So if you know about your sediment, you can plug all those values in and find what's the critical value that I need for momentary liquefaction to happen, which is essentially I will do if I had data. How do we get data? Well, I worked on creating this instrument here that we've built here at UNH. It's called the pressure stick. That's what we call it. It's fully autonomous. It's a vertical pressure profiling instrument. It has 8 pressure temperature sensors spread along the length of it, and about 70 centimeters in spread there, but you can see a concentration of them around the water sand interface right there. It samples at about 18 hertz, which is very fast, so it can actually resolve these processes of the momentary liquefaction potentially. At least that was the plan. So now that we have that and we have how we can do this, we can actually go to the field. So we work down at Wallace Sands Beach mostly. You can see us there putting the pressure stick in the sand itself. And because of the great tidal range here in New Hampshire, we can actually go at low tide and put this instrument in the sand. And then by high tide, it's covered with waves and water, and we don't have to get wet at all. You'll notice that our deployment times are January, February, September, October generally. So the best time to be at the beach is you can see us all bundled up in that far picture, but you know, it's fine. We usually work around storms. This top picture here was last October during a tropical storm we had here. The little dark sheep there is my old lab mate, Spencer. He's about 6'2", if you've seen him standing. So that's how big the waves were. I was not allowed in the water that day because I sit at about 5'1" on a weekday, so I was not allowed to go swimming. So yeah, it's pretty fun work in that sense. Here's another great shot of us there. There's Diane Foster and Baxter. That was our first deployment after COVID was allowing us to deploy, so we all had masks on. But yeah, so that's what the instrument looks like when it's actually at the beach. And yeah, to give you a quick run through the data, that's what the data comes back. You see nice waves in the 2-minute time series I'm showing you up there from 8 pressure sensors. Pressure's been converted to meters. So you can see that it does actually measure these nice asymmetric waves in the surf zone. And then if we calculate those vertical pressure gradients, we get something like this and can compare that to the critical value that I showed from that first equation. And what we're interpreting now is those passing those critical value is what we're seeing as momentary liquefaction. So next steps from there, I'm working on a second version of this pressure stick. It's actually being machined now, which will have more pressure sensors and hopefully be able to last longer, more battery power, essentially. And then, and working on narrowing down what parameters or factors actually cause this to happen more often.
How did you decide how long to make?
Some of it has to be with, so it won't come out of the sand when it's hit. So the bottom has to be a little heavier in that sense. And then how much of room we actually want it to sample over. That's 70 centimeters.
Is there kind of like a known distance that you get that liquefaction?
Generally, it's assumed to be about half the wave height. So if your wave height is,
So potentially a different area with higher wave
Mhm.
heights than.
you have one. So the approved version is going to have more sensors that go farther down. Potentially. Right now, we've only seen it in those top two sensors. If I go back the other way, the lines that pass these two lines are only our top two sensors in the sand. It's only about 16 centimeters. So it could be different.
Sensors in the sand.
Oh, it is. Should start one. You have a question back there?
Yeah, I was curious, did you guys like leave it overnight or anything like that?
So it can sample right now up to about 5 days running continuously. And we basically just leave it alone. We go check on it every low tide.
Was there any concerns about like with it or anything like that?
No, that's partially why we also play during January, February, September, October. When I first came, I was like, maybe I'm going like June, July. And my advisor was like, well, it's full of people June, July. I was like, oh, that makes total sense about why we go with this. Yeah, exactly. Yeah, we usually put marker buoys and stuff like that for safety, especially when sometimes these storm surfers do like to be out there, as well as signage and stuff on the beach. So we'll try to do the best we can.
Yeah.
No one's bought. We did have one GoPro one time running, and someone did come up and like look at it and saw it and like walk away because they didn't know what it was. So,
That's the same question I asked you back in February. Have you, with the second version, are you guys ever able to resolve actually the sand bed changing or no? Or
that's
is that the
another
dream?
thing I'm working on. That's supposed to be another instrument. We had talked about trying to integrate both of them, like using something on maybe the bottom of the big electronics canister facing down, but because it's the surf zone, it's hard to use acoustics, it's hard to use any sort of like optical sensor because there's bubbles and everything else to get a measurement of where the seabed is. My current vein of thinking is using phototransistors, which is like light levels. So kind of making an array that would sit next to this and try and resolve where it's lighter and darker and say, maybe that's where the sediment is. Because for now, we just assume at the beginning, we're like, oh, it looks like it's there. And then at the end, we come back and it's like, well, it's still there. So maybe it didn't move, but there has been one instance where it did come out almost about 30 centimeters of sand is gone.
Yeah.
So we're like, well,
Because I know that when we were doing this in Duck, they had like pretty intense like erosion going on over the whole
Yeah.
time. So
that one with the big waves up on the top, that one was like, we came out and it was like almost half out from where we had left it. We were like, well, we're gonna take it out now. We're not leaving it any longer. Again, like you said, we check on it every day and we were like, we're not gonna leave it any longer. It's 30 centimeters of sand is gone.
All right, so I'm Grant. I'm a fourth year PhD student in marine biology, and my advisors are Jen Mixes-Holds and Bonnie Brown. So my project focuses on identifying sentinel indicators of acoustic environments. And so what is a sentinel indicator? It's a measurable variable representing a system, process, or a key component of the ecosystem that is sensitive to environmental pressures and that can be quantitatively measured and monitored. So in the context of my research, the measurable variables that I'm looking at are soundscape properties and taxa that can be detected either through the soundscape or through genetic means. So the ecosystem component that I'm trying to relate these variables to is the acoustic environment, which in my project considers both soundscapes and the way that sound propagation is impacted in coastal areas. And so for those of you that don't know what a soundscape is, it's a characterization of the ambient sound in terms of spatial, temporal, and frequency attributes, and the types of sources contributing to the sound field. So you can have anthropogenic or human-generated noise, biological sound generated by marine mammals or fish, and geophysical sound sources like wind and rain. And so what I use to sort of quantify the soundscape is the soundscape code developed by Dylan Wilford, a previous student of Jen's. And basically what he did is developed methods or used methods of quantifying amplitude, impulsivity, uniformity, and periodicity of soundscapes. And so what I do is basically record acoustic data and then analyze that data to calculate these 4 metrics over certain periods. As well, in the future, I will use this data to identify marine taxa that produce sound. On the other side of my project, which is the genetic side, I do marine metagenomics, which is basically where you go out, you collect an environmental sample, you extract the genetic material from that sample, you amplify it with primers that are designed for certain taxonomic groups. So I started out with marine metazoans, and I'm going to expand that to include other groups. Sequence that data and compare it against a reference database. And basically what that gives you is a list of all the taxa that were present in your genetic sample or environmental sample. And so this is another way that allows you to detect marine taxa, and then you can overlap this with the taxa you detected with the soundscape to get a more complete idea of what organisms are present in an area. And so my data collection involved deploying hydrophones and collecting water samples, which you can see neatly in this picture, doing both at the same time there, in 3 different habitat types: macroalgae, sand, and eelgrass, at 2 different geographic locations. For this initial data, I expanded that to 4, which I'm finishing up now. And basically trying to decide whether more variability is emerging from the habitat type or the location in which the data is collected. And so the whole idea of this is the variability within each of these habitats or geographic locations allowing us to account for or discriminate between different soundscapes and acoustic environments. And the goal is to sort of do that by relating those 2 variables, soundscapes and metagenomic data, to elements that are expected to contribute to the acoustic environment, like the substrate, the taxa present, and the soundscape itself. And so this is, I'm really excited about this. I just processed this data yesterday, so it's very preliminary. But basically what we have here is a non-metric multidimensional scaling ordination. On the left, I did that ordination for my soundscape metrics. And so basically what I did is I calculated all of the metrics I described or told you about before, and pooled those together to basically see what amount of variability that's accounting for. And so I have my sites color coded. Yeah, sweet. Okay, so I got my blue shades here are the geographic location, and then each different shade or shape indicates a habitat. And as you can see, we have this really neat grouping by geographic location. So that's exciting. That means that at least there's some sort of spatial discrimination happening. And then if you look at this, there's even the eelgrass habitat sort of sticking out from these other clusters here. And depending on, I'll start playing with the different variables and seeing if there's statistical significance between habitats as well. But so then on the other side, we have the metagenomic data. And so each of these samples represents, or each of these points represents like 1 water sample and collected from the different habitats. And so here again, you can see we have this neat grouping by geographic location, not so much by habitat. And so I'm going to dive in and see which taxa are aligning really well with certain habitats, and vice versa for the soundscape, see which soundscape variables are aligning really well with certain habitats. Potentially use these to identify sentinel indicators of either habitat type or location along the coast.
With your metagenomic data, are you able to identify the species or species in general?
Yeah, good question. So I'm able to get down to the family level with these primers because I'm using pretty universal primers. They're not super specific to a certain group. Down the road, I'm going to include some marine mammal primers, some fish primers, and some aquatic plant species primers. And those will hopefully give me higher taxonomic resolution where I can maybe pull out some specific species. Thank you.
Afternoon, everybody. I'm a mechanical engineer, a little bit different, but I study oceans. I do sit here, and my area of study is AC interaction, as you could see. So recently, we went on a 21-day experimental campaign to University of Miami, and we did a bunch of wave formation and AC interaction stuff, which I wanted to share with you guys today. So right at the start, I want to share with you guys a storm event that we generated towards the end, because we were concerned if we'll break our equipment because of the wind forcing that we have. So you could see the sea spray, you could see all sorts of waves, all of them moving in one direction. So these are mechanically generated waves with I think 40 meter per second. 40 meter per second wind speed right at the surface, which is a storm event, not a hurricane, but a Category 5 hurricane event could also be generated in a facility like this. Now, this is the tank that we were working on. It's a pretty big tank. There are a few people around. This is the top of the tank, and we have 2 meter height or 6.5 feet depth, and half of it is for the air to flow, and the other half is for the waves, mechanical waves to be generated and flown. So this is a nicer picture of the tank. The inside of the tank actually looked like this on my camera. So the wind and wave direction are from inside of the picture to outside, and we were doing a bunch of things that we were doing a bunch of experiments. We were doing PIV along with infrared measurements of the water surface. So for airside PIV, we needed tracer particles and fog generator. Fogs were used as tracer particles for airside PIV. We were doing waterside. Some other group was doing waterside PIV along with LIF. We were doing infrared measurements of sea surface, of the surface temperature, and how cool skin layer or hot skin layer breaks because of turbulence present below the surface. But as you can see, this is the area where the air came in from, the air forcing came in from. The next area is the mechanical wave generator, through which you can control the frequency, amplitude, and everything else of the waves that are being generated. Our measurements specifically were from the top of the tank. If I go back really quick, so somewhere around here, we were looking down. So our measurements, so this wooden frame, not as pretty as the acrylic frame, was used because wood is a bad conductor of heat. So it doesn't reflect as much heat on the wood. So wood was an obvious choice. These are the 3 equipment. By the way, this was the direction of the wind. These are the 3 cameras, infrared cameras, high-speed infrared cameras that we were using. They were looking down at the surface of the water, and we were taking surface measurement. We were looking at how cool or hot skin layers are being broken because of turbulence, subsurface turbulence. A typical data set looked like this, where what you're seeing on the screen right now is a hot layer, hot surface skin layer, which are being broken by these thin black lines that you see are the skin layers being broken. Going back to our air interaction class, we'll do it there. Another equipment that was there, which I want to show, was a CO2 laser with thermal. So this right here. Okay, the one at the top right there is a CO2 laser, which does thermal marking, dots like these, right on the surface. So it prints those dots on the surface because they heat up, and your IR camera catches it because they are bright dots on not as bright surface. And now we need to look at like how they dissipate away or how they advect away. So a typical reading looks something like this. Our raw data would look something like this, where you can see like how the waves are coming in from this direction and how like those dots are being advected away, or that heat energy is being dissipated away from the turbulent kinetic energy because of the turbulence. So we were also doing PIV, and I just wanted to show this setup. So this is the PIV and LIF setup on both the side. Mark Buckley from a university in who's a student of Faberashii Viron. He was working on this along with this. So this is a typical LIF video that I took by like not looking at the laser, the classical laser, and then like having my phone look at it. But each event that you see is the laser flashing, and if you see like, I don't know if you could see in the first go, but like there's fog that you can see which looks at turbulence, and if your camera is flashing at the same time or capturing your images at the same time, you just see bright images, not the one that you see from my camera. But a few other equipments that were there were MARI FDIR, which is marine atmospheric emitted radiance interferometer. That's the Fourier transform infrared spectroscopy, which is to look at the infrared and take the Fourier transform and then like analyze the data. A lot of ocean mappers must use this, or not. But these are on the ships that process. MARI specifically is on the ship. Along with those, we also had UDM, which was supposed to measure the wave heights. We had Ergison for humidity and air velocity. We have WaveWire for wave height. And this is like another picture where you could see the only reason why I included that is because we had pitot tubes, WaveWire, and a few other things. I'll go through them really quickly. And based upon all these experiments, obviously the data that will come in will be analyzed a little while later, but just by looking at it, there are a few cool features that I wanted to show. So these are mechanically generated waves, and it was loud out there, on which there is air forcing. What I wanted to show over here is the wave field growing with the fetch. Now, the waves are very small, almost capillary size when it's closer to the entry point of the air, but then it grows as we go away from the entry point. It's wave field grows. Another thing which I wanted to show was the or the spray, not the sea spray here, but the spray at high forcing, at high wind forcing. You can clearly see like bubbles or small droplets of water flowing away from the surface. The last thing that I wanted to show was separated sheltering. So people who were doing LIF shared this. So this is a wave, and this is the direction of wind forcing on the waves. So you could see the streamlines or separated sheltering happening in this particular image or the image that was shared. This is the night sky of Miami. Thank you.
Hi guys, I'm Igor. I know I'm standing between you guys and Liberty, so we'll push through as quick as I can. So I work for Professor Maywin Payne. If you guys know her or her group, so we are called Manta Ray. In a nutshell, what we do is we have an ecosystem of a bunch of robots, surface, subsurface, that are all autonomous and in the process of being built. And currently, as we're developing this autonomy, there is really no reliable way for them to communicate to each other, especially underwater. So that's a chunk of work that I took on and I tried to resolve. So my project goal is to essentially have those robots talk as they swim next to each other. As we were brainstorming, trying to figure out how to do it most efficiently with least amount of cost. So light versus sound, those are really your two options underwater. Acoustics kind of went out of the window because it's expensive and complicated for those who have dealt with it. So we're stuck with optics. Now, next question is, do we use lasers? Do we use LEDs? Lasers are awesome, they're fast, but when you have a bunch of things swimming and moving in the water, it's very hard to point at something directly. So we stuck with I stuck with an LED. And then as far as a color selection, so these two, these are not my plots. They are, I got them from a couple of very good papers that sort of guided my decision towards which colors to choose. This one essentially shows light propagation based on the wavelength in different types of water. But the main point is you got to go somewhere with blue-green area. As you go towards like yellow, red, it dissipates very quickly. For those of you who dive, know that very well. You see nothing but a bunch of blue and green when you go under there. And then second, so this side shows essentially if we're deploying from the boat or whatever during the middle of the day, what is the ambient light like? And this shows we've got a lot of green that is likely going to blind our sensors. So we got to take that into the account also. In the meantime, purple is pretty good. So I decided to test 3 colors, purple, blue, green, and see how they perform and sort of march and build a communication system that way. A little bit of basics. So how does communication works, right? It's anywhere, any computer, it's all ones and zeros, 1 on, zeros off. And then we have a photodiode, essentially it's a photocell, you shine a light, depending on what color light, it generates a certain amount of current. And essentially you flash some sort of light, current, no light, no current. And then this is the transmitter. So out of that light, what I did is I built a carrier wave that has a certain carrier frequency and then combine it with a message and then light flashes the certain pattern. And here we go, we got ourselves a message. Now trying to predict that, I'm not gonna go into all of that because we're running out of time, but light propagation is still pretty complicated. So I assumed spherical spreading. And so we have an equation that some of you guys may have seen is based on turbidity coefficient and dissipation coefficient of the light based on the wavelength. And then I combined it with the spherical spreading and then came up with this thing. And it also involves duty cycle. Depending what your duty cycle of the light is, it's dimmer or brighter, that affects it also. And this is, and this ended up being, hey, this is what we think it's going to look like. Blue, green, purple, all theoretically look about the same in the ballpark. Now, how do we receive that stuff? This one is a little bit more complicated. I'll cover it in about 30 seconds. So photodiode that I showed you guys earlier receives the light with a bunch of noise and you get a really nasty signal and then got to filter it. So you build a band pass filter, it looks a little more proper, and then you straighten it out and you feed it into the board and then turn it into a digital message. So it looks something like this. So this was the filtered signal, and this is the signal that's going into the processing board. And then from now on, it's all computer science magic, right? And this was the receiver. So based on the gains of the transimpedance amp and then filter, this is what I came up with. Hey, this is what I'm expecting to see off of these colors. And all right, let's go ahead and test it. We packed up the transmitter and the receiver in the watertight tubes and spent a few days over the summer hanging out in an engineering tank. For those of you that saw me, I know I saw a few. And this one's going to be important. So flashing straight, we get reflection, either top or bottom. You really can't avoid it in a tank, which is going to skew the results a little bit, and I'll talk about it. And this is what we came up with. So blue and green, and then purple. I'm still trying to figure out what's going on with purple. That's an ongoing situation. And so if we look at the light, so blue came up pretty much exactly where I thought it would, except with this guy, and that's the reflection that I showed you guys earlier. It amplifies the signal a little bit, and then green's got the same scenario. Purple, I don't know. All jokes aside, I think a couple of thoughts. Either the light, even though the spec on the light is the same, it's a 10-watt light bulb, and it puts out about the same amount or draws about the same amount of current, but could be something with that, or it could be something with the photodiode. It's much less sensitive on the purple side of the house, so that could be something. And then this is the signal that we got across the engineering thing, so a bunch of stuff, and then we filter it out, and it's a bunch of zeros and ones that I can digitize and work with. So for short distance, robot to robot, should work just fine. And then a quick one. So once we process all that signal and get to this, so how do we resolve the network piece? So in a nutshell, all you do is use some sort of timing sequence. So this depends on your speed and your message size, of course. We know this is the length of 0, this is the length of 1. Let's get some kind of timer running and then recognize it with the board. And then the packet structure, essentially, you got to have some kind of starting sequence. So it's almost like talking on the radio, right? Let's say, hey, Joe, this is Bob. Hello, over. Works similarly. So you got to first give it a start sequence so the board knows it's not random noise, but an actual message. And then destination, address, sender address, and what you wanted to say. And this is just a quick example of a few hexadecimals that I sent. So interrupts, we have some kind of noise. Hey, we actually recognize that it's a legitimate message. And then a few test items here, and then the board times out. And as far as having multiple boards told, that's kind of the bread and butter of the scheme. It gets a little bit more complicated. Typically, you could use different frequencies, different filters, but if you have ROV swimming, you don't want to rig it with too many filters and frequencies. It gets expensive and very complex. So timer scheme is what I decided to go with. Essentially, once again, depending on the speed of the network and depending on the amount of robots in your network and the size of the message, what you do is you just divide, you start them all at the same time and it all got the timer going at the same time and you just divide it into chunks. So say if you have 3 nodes, node 1 listens from here to, I speak from here to here, and then the rest of the time it listens, and then so on for 2 and 3. And that's how they operate. And I got a pretty okay version tested in the lab and it worked. So that's where I'm at. Any questions?
Have you done any analysis of what kind of bit rates you can achieve?
Yes. So I think the limiting factor for me right now is the analog filter. Even the LED itself can go megabits. I'm working slow right now. I've got a 100K carrier and a 10 kilobit that I'm working with now, but theoretically speaking, I think you could push it to about just under 1 meg, and then after that, analog filters get complicated and slow.
Which color did you stick with?
Still picking that blue is the best one, but I do want to test purple outside. No, and as funny as it sounds, that's one of the experiments I got on my list over this month. I'm going to take all 3 colors outside, and I'm pretty certain green is going to get blinded during the day. Blue, maybe. I think purple with the narrow shape of the LED spectra and the fact that it's not enough of it, not much of it outside. I think it's going to be able to talk. So there is some use for all 3, depending on what you're trying to do, but probably blue to answer your question.
Cool.